contour integration. The integral is from 0 to infinity log of x over x square plus b square dx equal to pi over 2b log of b, where b is strictly positive. This we have to prove, and this is very important integral. So to solve this integral, we will integrate fz equal to, okay, what is our fz? In the numerator, I am having log of x, so fz becomes log of z over z square plus b square along the contour C, where C is the contour indented at. Now the contour is indented at z equal to 0. Why? Just take the denominator equal to 0. If I take z square plus b square equal to 0 and taking z square common, this will be 1 plus b square over z square equal to 0. And from here I get z equal to 0, and this b square over z square is negative 1, which means z is equal to plus minus b iota. So 0 is lying on the real axis, so the contour is indented at z equal to 0. And plus minus b iota, which pole lie inside the contour? Always the positive one. So b iota lies inside the contour. And one thing more, that this is the contour which is indented at z equal to 0, followed by the real axis from negative r to, okay, this is your semicircle gamma having the radius rho. So this point will be negative rho and this is positive rho, right? So we follow this contour from minus r to minus rho, and then along the semicircle gamma, and then from rho to r, and then from this semicircle tau, which is in the upper half plane, where this rho is tending to 0 and capital R is tending to infinity. And because the radius of the semicircle gamma is tending to 0, so this rho is always less than b, because b is given to be strictly positive, right? And rho is tending to 0 and b is strictly greater than 0. So which means rho is always less than b. And capital R, because it is tending to very large, it is very large and tending to infinity. So this is greater than b, right? Okay, so the poles of Fz we have just now calculated. The simple poles z equal to only b iota lying inside the contour. Now the next step is to find the residue of Fz at this pole, and the formula is just write the numerator as it is of Fz. So log of z over taking the derivative of the denominator, which is z square plus b square, at z equal to b iota. So this is log of b iota over the derivative is 2z, so this is 2b iota. Fine. All right. Now by Cauchy's residue theorem, this integral over c fz dz is equal to 2 pi iota times the calculated residue, which is log of iota b or b iota over 2b iota. Okay, let me write as iota b only so that there is no confusion. Okay, so this is equal to 2 iota will be cancelled out, so this is I over b and log of iota b. Fine. Okay, now this contour is split into many number of integrations, and this is equal to pi by b log of iota b. First one is we have to integrate along the x-axis from negative r to negative rho, then along the semicircle gamma, then from rho to r. Okay, so this is from negative r to negative rho. Write the function in terms of x because integration is along x-axis, and then along the gamma, this gamma semicircle, and then from rho to r. Sorry. Fx dx, and then from this tau, the semicircle bigger one, and writing that fz dz. Whenever you integrate along the x-axis, write the function in terms of x, and when you integrate along the semicircles, write the function in terms of z, right? So we have to calculate this one, and this integral over tau is always coming out to be 0. So now we are interested to find the first integral over tau, and I'm taking the mod because there is log present in the numerator, so we have to find out the absolute value of this integral. So this is equal to integral over tau fz is log of z over z square plus b square dz. Right. Okay, now because it is a semicircle, we take z in the polar form, which is r e the power iota theta, because the tau is having the radius r. So I'm writing z equal to r e the power iota theta, and dz becomes r e the power iota theta into iota d theta. So this is, I'm writing, okay, what are the limits then of theta? The limits are from 0 to pi. It is a semicircle, right? So this is log of r e the power iota theta over r square e the power 2 iota theta plus b square dz. And this is less than equal to 0 to pi integral log of r e the power iota theta mod. Sorry, I have to write the value for dz also. So this is r e the power iota theta into iota d theta. So this is mod of r square e the power 2 iota theta plus b square, and here I'm having the mod of r e the power iota theta, and then the mod of iota d theta. Mod of iota is 1. Mod of r e the power iota theta is, see, this is r e the power iota theta, this is r, and mod of e the power iota theta is equal to 1, right? And applying the inequality result, that mod of x plus y is less than equal to mod of x minus mod of y. So if you take the mod of the first one, r square e the power 2 iota theta, this will be r square only, that is 1, right? So this is further less than equal to 0 to pi integral. This is, okay, because log is there, so log of AB is log of A plus log of B. So this is log of R plus log of e the power iota theta is theta over, this is r square minus b square, and this is r, this is 1, and this is theta. Furthermore, I can write this as less than equal to, now what is the maximum value of theta? It is pi. So I can write again further less than equal to, I'm writing here the maximum value of theta, which is pi over r square minus b square r d theta. Now this complete thing, this one, this is a constant, and I'm lefting up with the integration of 1 d theta, which is theta, and putting the limits I get pi times this complete constant. So this is pi times the complete constant. Now this is tending to as r tends to infinity. As r tends to infinity, this tends to 0. See, the power of r is here square. And so this is tending to 0. Please remember one thing more. Because if r is greater than b, the denominator must be r square minus b square, not b square minus r square. Sometimes, for making the denominator positive, we interchange the terms in the mod only, so that when mod will be removed, we get the positive term in the denominator, right? So it is very important to note here that r square minus b square should come. Like when I will solve for the integral over semicircle gamma, there I am having rho instead of r. So it is very important to notice that it should be b square minus rho square in the denominator, because b is greater than rho, right? This is very important. Here it is as it is, simple one. But in this case, I will be changing the terms in the denominator to make the denominator positive, right? So for this integral, just taking the mod, this is fz is log of z over z square plus b square dz, where z is now rho e the power iota theta, where rho is a radius of this semicircle gamma. So this is equal to, now the limits are from again 0 to pi, it is a semicircle. So this is log of rho e the power iota theta over rho square e the power 2 iota theta plus p square into dz is rho e the power iota theta iota d theta. So this is less than equal to 0 to pi integral mod of log rho e the power iota theta and mod of rho e the power iota theta mod of iota d theta. And in the denominator, this is mod of rho square e the power 2 iota theta plus b square. Now when I apply the result, I will be getting rho square minus b square, right? So because I need b square minus rho square, so I'm just interchanging these terms. I'm writing b square first. It doesn't matter in this step. It is very okay and fine, right? So this is further less than equal to, by applying the result, this is log of rho plus theta, and this mod is rho, and this is 1 over b square minus rho square. This is what I was going to notice to you. So this is d theta. Alright, okay. Furthermore, the maximum value of theta is pi. I can write that less than equal to, writing the maximum value of theta here. So this is further less than equal to 0 to pi log of rho plus pi. And in the denominator, it is b square minus rho square rho d theta. Now this complete is constant. Taking this outside, and this is just integrate 1 with respect to theta. This will be pi times, right? So this is equal to, I'm writing rho first, pi times rho log of rho plus pi over b square minus rho square. Fine. Okay, taking this sum, so this is log of rho plus pi square rho over b square minus rho square over b square minus rho square. So the denominator should be positive, right? So this both will tend to 0 as rho tends to 0. Please see in the numerator of the first term, if you apply limit rho tends to 0, then rho log rho is 0. Fine. Which means by letting limit r tends to infinity and rho tends to 0 in the first equation, we have these two integrals which are tending to 0. So marking this as 1 and letting r tends to infinity and rho tends to 0 here, right? So letting rho tends to 0 and r tends to infinity in 1, we get second and fourth integral vanishes, rest remains with, because r is tending to infinity, so minus r will become minus infinity to 0 because rho is tending to 0. So this is f of x dx plus 0 to infinity f of x dx equal to pi over b log of iota b. Okay, so this implies merging these two, minus infinity to infinity, f of x dx equal to pi over b log of iota b. Writing the value of fx, log of x over x square plus b square dx equal to pi over b log of iota b. Now we have to equate the real parts. For that we know that, please note this result, that log of x equal to log of mod x plus iota argument x, where this incomplex number, if you're having z as your complex number, that is a plus iota b, then log of z is equal to log of mod z plus iota, and the argument of z is tan inverse b over a. So for the complex number we write the result as, for log as this. So when you equate the real parts, you must have log of mod of the complex number, right? Mod of the variable. Now here I'm having x, but imaginary part is 0 for this x, for this number. So equating the real parts, we get minus infinity to infinity. Please take log of mod x. But if you have circle, if you are having for the circle, because this is for if z is a plus iota b along the lines, but for circle we have z equal to r e the power iota theta, right? So this is log of z equal to log of mod z. Mod z is mod of r e the power iota theta, which is log of r only. So this becomes r plus iota. This is argument of z, and argument of z is theta. So write here theta. So because this is our case for the semicircles, so we must focus on this second one. So the real part for log of z is log of mod z. So write down, if you want to equate the real parts, write down log of mod x over x cube plus b square dx, and this is equal to pi over b. This is log of iota b, again a complex number, so write down the real part as log of mod iota b. Is this thing is clear? Okay, so for the real part you just have to take the mod, right? So this implies this is minus infinity to infinity log of mod x over x square plus b square dx equal to pi over b log of b, because log of iota, mod of iota is 1, so pi over b log of b. And because I have not written log of mod x as log of x, because I know that this is my even function, because I need to change the limits of the integral. So that is why I have just written log of mod x as it is in the numerator, because I need to change the limits. So this becomes, because this is my even function, this will be from 0 to infinity twice, right? So this is 0 to infinity twice log of mod x over x square plus b square dx equal to pi over b log of b. And taking this 2 to the other side, now I can write 0 to infinity log of mod x as simple log of x, and this is x square plus b square dx equal to pi over 2b log of b. Hence the result